Hello again. We are going to continue with Module 9 and look at more of quantum mechanics. So let me share my screen. So when we were talking before, we showed that electromagnetic radiation had properties that were wave-like. So they had a wavelength and they had a frequency and they diffracted. We also showed that light had properties of a particle. They exhibited the photoelectric effect, which means that I have these quantized packets of energy that are being emitted when I actually excite an electron and then have it decay. So we know that light has both wave and particle properties. This is called the wave-particle duality. So light exhibits these wave-like and these particle-like behaviors. Now, in 1924, de Broglie suggested that if light can behave in some respects like matter, maybe matter can behave in some respects like light. So he wanted to look at that, he wanted to see if maybe matter isn't just particles in nature, but maybe it has some wave-like properties. So what he actually found is this equation, which is called the de Broglie equation. This allows us to calculate the wavelength of a particle. Usually we do this for electrons, but it could be any other subatomic particle. It could be an object like a baseball or a car, right? All I have to know is the mass and the velocity, and then this is Planck's constant. And remember, this is joules second. So my mass must be in kilograms, and my velocity must be in meters per second. So mass cannot be in grams, it has to be in kilograms. So what de Broglie found is that electrons actually behave like circular waves oscillating around a nucleus. There's no defined stationary end, and the circumference is the energy level times the wavelength. I have these stable circular waves in these various n values. Now, using his equation, I can actually calculate the wavelength of any object in matter. So we're going to do it here for a car. So the question is, what is the de Broglie wavelength in meters of a small car? Now, cars are big. I have much bigger than an electron. Remember, that's like times 10 to the minus 27 grams. Here I have over 1,000 kilograms traveling at a velocity of 24.6 meters per second. So this is in kilograms. If it's not, I have to convert. This is in meters per second. If it's not, I have to convert. Here is my H. Now this unit is joule seconds, because 1 joule is equal to a kilogram meter over seconds squared. So if I look at this unit and then I add a second, or meter squared over second squared, what I end up with is this unit, which is a joule second. Okay, so when I plug my values in, this is what I find out that the wavelength is. So a car actually has a wavelength of 2.34 times 10 to the minus 38 meters. Now this is so small, it's negligible. And we don't actually, think about wavelengths with traveling cars. But if this particle gets really, really, really small, then my wavelength gets much more significant, and it's actually pretty interesting. And this is what we do in quantum. It's like we can compare things to classical physics, right? In classical physics, all of these large objects, have these equations that we can actually calculate these different parameters like we do with small objects. But in the large macroscopic world, those values are so small that we get that it doesn't matter at all. However, when I think about the width of an atom, the wavelength in an atom can be just as large as the atom itself, which means it's much, much, much more significant. So let's look at this in a practice problem. Protons can be accelerated to speeds near that of light in particle accelerators. So I'm going to estimate the de Broglie wavelength. Now I'm doing nanometers of such a proton. So here is my velocity of the proton, and this is 10 to the 8th, not 108. This is minus 27. I have lambda equals h over mass times velocity. So this is just velocity, not mu. I have 6.626 times 10 to the minus 34 joule second. I have a mass of 1.673 times 10 to the minus 34 kilogram. This is what I want because of the joule. The joule has kilograms in it, like I told you on the slide before. Whenever I have a constant, any units that go towards making that constant have to be the units that I put in there, otherwise it won't cancel out. So, and then my velocity is 2.90 times 10 to the 8th meters per second. When I do this in my calculator, what I'm going to find out is I have 6.626 minus 34 divided by 1.673 minus 27 and then divided by 2.9 to the 8th. And what I get is 1.3657 times 10 to the minus 15th meter. Now, compared to the size of a proton, right, that's significant. And then I want this in nanometers, so I'm going to say for every 1 meter, I have 10 to the 9th nanometers. So I'm going to multiply by 1, and I'm going to get 1.367 times 10 to the minus 6. And that's in nanometers. So that's a very, 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 very small wavelength. Now, proof that the electron had wave nature came a little bit later, and this was through a demonstration such that when I took an electron source and I threw it and I sort of aimed it at this barrier with the slits, I actually got an interference pattern the same way that waves do. So electrons themselves present this interference pattern which suggests that they behave like waves. So electrons can diffract. Now here's the problem. The proof this is what was expected to happen because my electrons are particles. If my electrons are particles, they don't diffract and they're going to go straight through those two slits and they're going to only produce two spots. So if they only behave as particles, there would only be two bright spots. But what we found is that they actually diffract and they actually show this interference pattern. So now we can conclude that they act like waves. So the issue is when you try to observe the wave nature of the electron, you cannot observe its particle nature and vice versa. Because if you actually do this experiment and you set it up to observe the wave nature, you actually only get those two bright spots. So remember in the beginning when I said the act of observing actually changes the behavior? This is what we see with electrons. When I try to observe the wave nature, I can't observe its particle nature. When I try to observe its particle nature, I can't observe its wave nature. So I can set up an experiment where I see the interference pattern, and I can set up an experiment where I see that position with those two lights, right? The problem is the act of observing actually changed the behavior. So these are called complementary properties. If I know more about one, I know less about the other. So I can't actually observe them together. I can observe one or the other. I can't observe them together. Now, about the same time, Schrödinger proposed a quantum mechanical model of the atom, which is focusing on the wave-like properties. Heisenberg stated that it's impossible to know precisely where an electron is and what path it follows. This is called the Heisenberg uncertainty principle, which even if you don't understand, you've probably heard of this, hopefully. So Heisenberg stated that the product of the uncertainties in both the position and the speed of a particle is inversely proportional to his mass. So this is the Heisenberg uncertainty principle in a mathematical description. So this X value is the position. The delta X is the uncertainty. Remember, I could have a delta X that's really large or really small. That's the uncertainty. This velocity is a given value. My delta V is going to be the uncertainty. I can have an uncertainty that's really large or really small. So this can also be considered momentum, and that's given P is equal to mv. So my delta P is equal to m times delta V. So sometimes when you look at the hydrogen or the uncertainty principles, this m delta V is going to be looked at as momentum or an uncertainty in momentum. So when I take the uncertainty in my position, now the mass doesn't change, and I multiply it by the uncertainty in the velocity, I'm going to get greater than equal, this is Planck's constant. And I can solve for uncertainty. I can solve for delta V. I can solve for a lot of different things because these are just variables in an algebraic equation. But the ultimate thing is, this means that the more accurately you know the position of a small particle like an electron, the less you know about its speed and vice versa. So if I know something, one of those things with some certainty, I have no idea about the other thing. So this is an equation that's used a lot. Now, this is what we were talking about before. When I have this electron source and I have my slit, and now I put this laser beam here, this experiment is designed to detect the single electron particle. So what I see is the results for the single electron particle, and I get no interference pattern. So this shows Heisenberg's uncertainty principle. If I can observe the particle, I don't know anything about the wave. So this comes back to these two terms, determinacy versus indeterminacy. According to classical physics, particles move in a path which is very easily determined if I know the particle's velocity, the position, and the forces acting on it. So I can, something that acts with determinacy has a definite predictable future. So again, my baseball, when I throw my baseball, it's very predictable based on the velocity, the position, and the forces that act on it, where that ball is going to fall, right? However, when I go into that world of the very small, I cannot know both the position and the velocity of an electron at the same time. So I cannot predict the path it will follow. So this is called indeterminacy. I have an indefinite future. I can only predict the probability that something is going to happen. So the best I can do is to describe the probability that an electron is going to be found in a particular region, and I'm going to do this using statistical functions. Now, we are going to use these equations to solve various parameters, but we're not going to go in and prove a lot of this stuff. We're not going to use goodwill hunting math, you know, the kind of math that people go to graduate school for and whatnot. We're just going to use the basic equations, and you should know what they mean. Here's trajectory versus probability sort of outline. When I have a large object like a baseball, it follows this classical trajectory. I know at any point on this trajectory where that baseball is going to be. This is a quantum mechanical. This is a probability distribution map. This particle, like if I throw it, has this probability map. Anywhere the blue dots are more intense, I have a higher probability. So the probability that it sort of follows that same arc is high, but there's also probability that it's going to be anywhere else in this map of probability. So what I can say is that there's a high probability it's going to act here. There's also a probability that it's going to be, right? So there's a high probability that I'm going to fall in this area, but there's still a probability that I'm going to be outside of it. And as I go through it, maybe this is the 20% certainty. And if I look at 70% certainty that the particle is going to be in this area, I have to go way far out. And then it sort of goes on. So this is the quantum mechanical strike zone. I have the number of particles that are the distance from the center of the strike zone. So as my distance goes out, right, my probability of finding a particle is much lower. But there is probability for a good long while as I go. So my strike zone is much less predictable. And there is a indeterminacy of that position of that electron. So here's an example of how I'm going to use this. I have delta x times m delta v. And let me get the right formula. Greater than equal to h over 4 pi. This is my uncertainty principle. So notice I have this delta P. Remember, my delta P equals mass times delta V. The uncertainty in the momentum of a football thrown by Tom Brady during a Super Bowl. So this is the velocity. There's just one of these. I have 40 meters per second as my velocity, right? The uncertainty is 1 times 10 to the minus 6 of the momentum. The mass is 40 kilograms. What is the uncertainty in position? So this is what I want to solve for. So my momentum is mass times velocity. So that's going to be 0.40 kilogram times 40 meters per second. So that momentum is going to be 0.4 times 40, or I get 16 kilograms meters over second. So that's my P. My delta P is going to equal 1 times 10 to the minus 6 times my P, which is 16 kilogram meter over second. So this is my delta P. I have that value times 1 to the minus 6. And I get 1.6 times 10 to the minus 5th. Remember, this whole thing is my delta P. So now I have values, right? What I have is delta x, and I'm going to divide through by delta P, is greater than or equal to h over 4 pi delta P. So it's greater than or equal to 6.626 times 10 to the minus 34 joules second, which is, let me use the other one, kilogram meter squared over second squared times second, divided by 4 pi times 1.6 times 10 to the minus 5th meter second. So now my delta x, oh, this is kilogram meter second. So that cancels with that. One of these cancels with that. This and this cancel with that. And what I'm going to get is kilogram, or I'm going to get meters. So when I do this math, I find 6.626 to the minus 34 divided by 4 divided by pi divided by 1.6 to the minus 5th. And I have my delta x is greater than or equal to 3.30 times 10 to the minus 30 meters. So think about that. This is an extremely small uncertainty. So I know where that football is going to be. Lucky for Tom Brady, right? Unless he deflates it anyway. This goes to show you with large objects, right? I don't have that uncertainty, and I can prove it using this principle of quantum mechanics. The uncertainty is negligible. I actually know where that football is. So compared to the mass and the size of the football, the uncertainty and position of that football is very, very, very tiny. Now, if I were to do this for an electron, I would find that the uncertainty position is really large compared to the size of the electron. And that's actually an interesting question that sometimes I like to ask, is if you compare the uncertainty of a baseball to the uncertainty of an electron and uncertainty in position given everything else, what does that tell you? At this point, we are going to go a little bit further. Remember that electron energy and the position are complementary properties. When I think about the electron energy, I can use my regular kinetic energy, which is equal to 1/2 mv squares. So for an electron with a given energy, the best we can do is describe a region in the atom where I have a high probability of finding it. Many of the properties are actually related to the energies of the electrons. So we are actually going to stop here. And then when I come back, I will continue with the rest of, or with more of Module 9. Okay, goodbye.